Welcome to The Explainer. Today we're going to put on our detective hats and solve a really cool two-part linear algebra mystery. And this one comes straight from question 5 of an exam paper. So let's just jump right in.
All right, so our first case here is all about something called orthogonal complements. Now, if you're not familiar, the easiest way to picture them is like a subspace's total opposite, kind of like its antispace. So here's the mystery we need to solve. We've been told that two subspaces, let's call them U and V, well, they can't possibly add up to fill all of space if their antispaces happen to share a secret non-zero vector. And our job? We've got to prove it.
Okay, so what does this orthogonal complement thing really mean? Well, the main idea, the really crucial point, is that any vector in what we call U perp is totally incompatible with every single vector inside of U. They're orthogonal, right? Meaning they meet at a perfect 90-degree angle, and if you take their dot product, you always get zero.
Now, this whole investigation, it all comes down to one single critical clue. There's this non-zero vector, we'll just call it W, and it's an outsider to both U and V. In other words, it's sitting in U perp and it's sitting in V perp. This little shared vector, that's the key to everything.
This is where things get really clever. We're going to use what's called a proof by contradiction. Basically, we're going to set a trap. First, we assume the opposite of what we want to prove. Let's just pretend that U and V do add up to fill all of space. Okay? So if that's true, it means our special vector W has to be made up of a piece from U and a piece from V. So W equals U plus V. Now watch this. Let's find the squared length of W, which is just its dot product with itself. That's W dot U plus V. And if we distribute that, we get W dot U plus W dot V. But wait a minute. We know W is orthogonal to everything in U. So W dot U is 0, and it's orthogonal to everything in V. So W dot V is also 0. So we get 0 plus 0. This means the length of our vector W is 0. But that's impossible. We were told W is a non-zero vector. The only vector with 0 length is the 0 vector itself.
See? We've walked ourselves into a complete contradiction. The only way out of this logical mess is to admit our starting assumption was just plain wrong. So U plus V times cannot equal all of space. And boom, just like that, case closed.
All right, let's move on to case file number 2, the case of the defective matrix. Now, if our first case was about the big picture, how whole spaces interact, this one gets way more specific. We're zooming in on a single matrix, and we're on the hunt for the exact conditions that make it defective. And defective is just a fancy way of saying it can't be simplified into a really nice, clean, diagonal matrix.
And here's our suspect, matrix A. Take a look. You'll see there's an unknown variable in there, A. Our whole mission is to figure out what specific numbers can we plug in for A that will, well, break this matrix and stop it from being diagonalizable.
So, how are we going to crack this?
Well, this slide gives us our game plan. The whole idea of diagonalizability boils down to this. For every special value in the matrix, called an eigenvalue, two other things have to match up perfectly. First, it's algebraic multiplicity, that's just how many times that eigenvalue shows up, and second, it's geometric multiplicity, which is about how many independent eigenvectors it has. If they match for every eigenvalue, you're golden. The matrix is diagonalizable. Our job is to find the exact values of A that cause a mismatch.
First things first, we need to find those eigenvalues. And to do that, we have to find something called the characteristic polynomial. You can think of it as a special formula we get from the matrix, and it basically holds all the secret codes to its most important properties.
So we do the calculation, and this is what we get. The roots of this polynomial are the eigenvalues we're looking for. And you can see them just by looking at it, right? Our eigenvalues are going to be A, 2, and 6.
Now here's a super helpful shortcut. If A is any random number that isn't 2 or 6, what do we have? We have 3 totally different eigenvalues. And here's the rule. Any matrix with distinct eigenvalues is always diagonalizable. No questions asked. So we don't need to worry about those cases. The only time we might have a problem is when the eigenvalues repeat, and that only happens in 2 specific scenarios, when A is 6 or when A is 2. So those are the only 2 cases we need to investigate.
Okay, time for the main event. We've narrowed it down to our 2 suspects, A equals 6 and A equals 2. Now we just have to check them and see if they really do cause that critical mismatch between the multiplicities.
Let's kick things off with our first case, A equals 6.
So if A is 6, then the eigenvalue 6 shows up twice, right? That gives it an algebraic multiplicity of 2. The big question now is, what's its geometric multiplicity? Is it also going to be 2?
Okay, to find that geometric multiplicity, we have to figure out the dimension of the null space. It sounds complicated, but it's just the collection of all vectors that this new matrix, 6i minus a, would squish down to 0. So we set up that matrix, and then we simplify it using row reduction. This helps us see what's really going on under the hood.
And after we do that row reduction, we can see the rank of the matrix. That's basically the number of non-zero independent rows is 2. The geometric multiplicity is super easy to find from here. It's just the number of columns, which is 3, minus the rank. So 3 minus 2, that gives us a geometric multiplicity of 1.
And there it is. That's the smoking gun. The algebraic multiplicity was 2, but the geometric multiplicity is only 1. They don't match up. So that confirms it. When A is 6, this matrix is officially defective. It's not diagonalizable.
Okay, we've got one culprit. Now let's check our second suspect. What happens when A is equal to 2? Well, same story, right? The eigenvalue 2 now has an algebraic multiplicity of 2. So let's see if the geometric multiplicity will play along this time.
We're going to run the exact same playbook here. We set up the new matrix. This time, it's 2i minus a, and we perform our row reduction to find the rank. And would you look at that? It's the exact same result. The simplified matrix has a rank of 2. So our geometric multiplicity is, once again, 3 minus 2, which is 1.
And that's all the confirmation we need. Algebraic multiplicity, 2. Geometric multiplicity, 1. They don't match, so we've found our second culprit. When A equals 2, the matrix is not diagonalizable.
So there you have it. Our investigation is officially complete. We've checked all the leads, analyzed the evidence, and we've found exactly what we were looking for. So let's just sum this all up. We've proven that matrix A is defective or not diagonalizable if and only if that little parameter A is equal to 2 or 6. For literally any other number you plug in for A, the matrix can be perfectly diagonalized. Case closed.
And that kind of leaves us with one final thought, doesn't it? I mean, this can all seem like just a bunch of abstract numbers on a page. But these properties, like whether a matrix is diagonalizable, this is the mathematical bedrock that people use to model the real world. We're talking about determining the stability of a bridge, predicting the behavior of quantum particles, even forecasting long-term trends in the economy. It really makes you wonder, right? How do these fundamental, kind of hidden mathematical rules actually shape the incredibly complex world all around us?